All right, I actually typed up a series of slides I was going to use for today, but I synchronized in OneDrive, which doesn't seem to be working. I'm going to be working without the benefit of all my teaching prep, so it's going to be kind of as I go along here. So I guess the easiest way to cover this is to basically look at that there. I don't know if I've got the same version of MATLAB as you do. Which version do you have here? I'm going to go ahead and bring up MATLAB. But what we're going to cover today is just how to plot with MATLAB. So I'm going to break this up into individual groups, the topics that we have. As I understand, your instructor is using this. Does everybody have a copy of this thing from University of Dundee? Or is it, or not? What are you using for a book? You don't have a book. Is that what I'm seeing? Okay, all right. I will go ahead and post this, but this is actually a very skippy little tutorial. There's nothing wrong with it, but this is what she's basically been covering, or told me that she was covering. It's from this document right here, and I'm going to probably add more things to that as we go along here. So this is MATLAB version 2013A. What version do you have on your computer? I saw a few of you bringing it up. What's that? 2014A? Okay, I'm a year behind, so that's all right. Actually, I'm running this off my computer that I brought from the U.S., and it's been about a year since I've taught this particular subject, so it would make sense that I'm a year behind. I'm going to not spend time uninstalling it and reinstalling it between now and the end of this session. So I'll be running this here. Everything should work exactly the same on your computers as what we're going to do. So what I'm going to basically do, and I'm going to be checking to see whether the plots are there. If not, I will possibly go to some websites that I stole the things from my slides yesterday. I don't know why I didn't copy it onto a thumb drive instead of relying on the internet to. Yeah, see, eventually a directory will come up there and say MATLAB, but it's not there. It's still synchronizing there. If I right-click that there, it'll tell me that it's somewhere. Right. Supposed to, if I right-click that, scan drive. No, it's still it's synchronizing. That little, the little yellow thing tells me that it's not there. So let me just kind of go through here. And the plot command is really very straightforward in MATLAB, right there. So, and of course you will be tested on some of this material. But basically what we're going to be doing is setting up a couple of functions and just plotting them. And they're very straightforward here. First thing I'm going to do, and I'm not going to do this, I'm just going to, if I make a mistake, it's because I'm doing this without the aid of my notes. I'm doing this from memory. But if I look at this right here, and actually I'm aided a little bit by my command history, but if I want to say plot a function, and the function I'm going to plot is just simply a simple sine wave from 0 to 2 pi, or let's just do 2 cycles, we'll go 0 to 4 pi, so we can see what the sine wave looks like if we So first thing we're going to do is we're going to set up the time and the way we do that is we just simply say our t is equal to 0, colon, and let's just say pi divided by 30. That simply means that it's going to create a 30 points. That's a time in between our 2 points. Because what we're setting up is an array. And this array is going to be our sine wave. And our sine wave, let's see if I can put there. Where's my OneNote here? It's still synchronizing. Oh, where's OneNote? Let's bring up my OneNote here. There, as you can tell, that's early on a Monday morning, and OneNote I thought should. Oh, there it is. There. I actually use another computer, but I don't have MATLAB on that computer. But as we look at this, no, we will not upgrade this. What we're plotting here is from 0, and I'm going to say 4 pi. Now, a sine wave, of course, has a period of 0 to 2 pi. But everyone here knows that, right? Right there. So a normal sine wave looks like this. And when I did that pi divided by 3 means, or 30, means between here and pi, I'm taking 30 data points right here. The time between each data point is pi divided by 30. That's the period between delta t between the two data points that we're taking right there. So that there. And I don't know how far she's gone this far, but I'm just going to kind of review everything as I go through this here. So if I'm repeating information you already know, I'm sorry. If it's new information, you need to know it. That there. So going back to my OneNote here, so we divide pi by 30. That's our time between that, and then we want to go to 4 times pi. In other words, that there. Now I put a semicolon at the end of this. If I don't put the semicolon in there, it's going to put a whole bunch of data. It's going to show me the data that it generates. The semicolon just simply suppresses the output, is what that's doing right there. So that creates that right there. And now we're going to create our function. And our function is just going to be very simple. Let's just say y is equal to the sine of t right there. So all we're doing is we're just creating a sine wave right there. And our next step is we just simply plot it. And the plot command is very simple. We can say plot x and t and y. Now when we do that, that places t on the x-axis and the y on the y-axis right there. So, and this just simply shows a plot. I don't put the semicolon on there, and that there, and I just hit this, and it should just bring up a plot that looks like that. So it's very straightforward. Now we could do a lot more things with this right here, that there. But that's our basic, easy way of plotting a sine wave. I can turn right around, and I'm going to minimize this, and there's another function which I'm going to say hold on, right there. And what hold on does is keeps that plot there and allows me to put the next plot on that there. So I'm just going to say y2 is equal to, and I'm going to say sine, and I'm going to say 2t. So this is going to double the frequency. And then I'm going to say plot t y2 right there. And with a little luck, what we should see is 2 sine waves here. I've just added the second sine that there. If I don't put the hold on, so let me just clear everything. Let me close this. I'll just clear right there. And then I can hit the up arrow to repeat my commands. So it does help a little bit. Is the up arrow on your keyboard allows you to repeat the commands. So I'm just going to go ahead and put that back in there, right there. And before I do that, I need to say right there. And I plot that again. It shows the same plot. Now, if I move this over to here, and if I just put do the second plot again, right there. Right there. Notice that it wiped out the previous plot. So the hold on allows you to keep the same data there, right there. So it's a very simple thing to do if you want to plot 2 things. Now, there's a lot of things we can do with the plot command, and unfortunately, I said I didn't prepare well for this. Let's see. Why is OneDrive not doing its thing here? Now, these tools are supposed to help you view sync problems. Right there. What's our sync problem here? Right there. Supposed to synchronize. Maybe I didn't log on. It says it's synchronized. Let's see if I can pull my notes down here. It could be that I'm not logged in properly. Right there. Nope, that's not going to do me any good. Hopefully this will give me access to my files. If not, I continue faking it. Yeah, okay. Okay, here we go. As I said, that's what happens when you rely too much on technology. It messes you up, and when it doesn't work like it's supposed to, you've got that there. Okay. And I want to download this here instead of and wrong place. Let me download these right here. Shouldn't take me long. I was supposed to try to do this before class, but it's supposed to do this automatically. Whenever I turn it on, it's supposed to go grab the files from the web and stick them on this computer, but let's just download this one separately. Oh, it's going to. And these files aren't very large. I don't know why. Okay. All right. Now I can act like I know what I'm talking about because I've got my cheat notes right there. So basically, this is the same example that I just did, and that's there. Now, you can also do what I did in this particular example. Instead of doing the hold on, you could tell it to plot both at the same time right there. So in this particular case right here, I could go back to my slides here, and again, let's just close this here, and let's just clear everything, and I can go through and say t is equal to 0, comma pi divided by 30, 4 times, we'll just say 2 times pi. We'll just do one cycle right there. We can say y is equal to 3 times sine 2 times t right there. So we're going to get that there. And I can say y2 is equal to 6 times cosine 3 times t plus pi divided by 2. In other words, we could put an offset there. In other words, give it a phase shift right there. And I could do plot t, y, t, y2 right there. And notice that we now have, there's our two plots shown simultaneously. The advantage of doing it this way, of course, it automatically picks up 2 different colors right there. So there's multiple ways that you can plot 2 plots on the same plot. You can either put the hold on, which keeps the existing plot there and just adds this plot to it, and it automatically rescales it, or you can just simply tell it to plot multiple plots at the same time. And you can do this up to, say, 10 times if you want to put 10 different graphs on the same plot right there. So it's a very easy tool in order to plot that there. Now, I know that the first half of this course you spent a lot of time programming. Everything that I'm doing here could be included in what they call an M file, where I can write this and just execute the M file. I can create a M file with my commands and create that there. Have you created M files yet? The term M file doesn't mean anything right there. So that's there. I will probably not cover that there. You're looking at each other like that there. So I have to assume she has not. And that's the problem with jumping in the middle of a semester like this, is I don't know what was covered and what was not. And of course, I've discovered with the students, and I've been teaching for 30 plus years, that if I ask a group of students if something was covered, they always say no anyway. That's the flat answer. Did you cover how to add and subtract yet? No. What do you mean by add? It's not quite that bad, but that there. So, all right, but that's the basic plot command, and really the rest of the time we're going to be here is, and I didn't bring my charger for my computer, which is a good time to end the class. If I start getting the end of battery command, it's time to wrap up. But we'll get through everything before that there. Besides, I'm actually just next door, so we'll go get the charger if I want to. That there. All right, let me go back to my slides a little bit. That there. But that's the basic, simple. That there. Now, the next thing we can look at here is we can also specify colors and line types if we want to, right there. And I'm going to be basically, and I'm going to cheat. And the way that I cheat is that I'm going to grab this and copy it right there. And the reason I'm doing that is that it actually makes it a little easier for you to see right here. So let me talk about what I just plotted here. What I just plotted right here. Right there. So let me clear this and do it again. Clear. Right there. What's the command for clear this command window? I always forget that particular one. There's a command for clearing the command window. Right there. You probably covered it and you probably remember it faster than I do. Right there. But that's there. But regardless, we'll just work with it right here. Okay. Let me just simply paste that again. Right there. And let's go through. The reason I pasted this again is that it is to go through here. First off, I did the same thing. The command, all I did was set up a linear space right there. And I didn't call it line space. I just simply said that x starts at 0. The data points are pi divided by 10 apart from each other. And you can see what happens when I make that 20. That means that here, and what's kind of interesting, if we look at this particular plot, and these are 3 plots where we've offset the sine wave. The middle one right here, this is the actual sine wave, the green one right here. You see the green one here? That starts at 0. And then I've got 2 others that I offset here a little bit, and you can see that there's a phase shift between that. And I know that you've had basic math, so don't tell me you haven't seen phase shifts yet, right? You've seen phase shifts right there. So I offset the first one by a quarter of, 0.2 pi. And for those that don't remember pi, pi is equal to 180 degrees. So if I take a quarter of that, so half of that is 90 degrees. So 0.25 is what? 45 degrees roughly? Right there. So, or you can just always pull up your calculator. Right there. And you can take 0.25 times 180. That tells you that that's a 45 degrees phase shift right there. Then the next one is over here is pi. It's got a 0.25 or 0.50, so that's a 90 degrees phase shift right there. So I can also offset it by pi, which is going to right there. And we'll play with some of those here in a minute. That there. So the next thing that we've got going here is that we're going to tell this the color that we want this line to be right there. So as we look at this command here, and it's kind of hard to see, I'm looking at this right here. As I said, I'm recording this so you can go back and watch the video. If you know, I'm assuming that the reason I record this is I want you to look at the screen, not trying to write everything down frantically. So this whole lecture is that there. You can go back and take the notes there and try this. So the color command. Now this color command comes from right here, and we may have to blow this up right here. This specification right there. Yeah. Let me just hit the slideshow. Let's from current slide. All right, as we look at this right here, is that we've got these three values here, and these are the easiest way to look at it is these are the RGB. Everyone see these three lines right here? Weren't there? One RGB. This is the value between 0 and 1 is the red component of the color we want. This is the number between 0 and 1 of the green component, and this is the number up there. We could come up with any color we want, because red RGB means we could come up with about 2 million different colors. Yeah, that's there, by setting up our values. Now, there are built into this a number of colors that are already built into it, and we can just use Y, M, C, R, G, B, W, and K, and we can get those colors. Or we can specify specific colors we want. So the color command is very, very flexible. You can do whatever color we want right there. The next is our line type, and I got a similar slide for that there that goes over the various, and I didn't bring my little, actually I don't have batteries for my little laser pointer here, but as we look at this here, if we want a plus symbol, we just use the plus symbol. If we want the circle, that's the little degree symbol there. You can put that there. Asterisk, point, dots, X's. We can put in a quote, S for a square, D for a diamond. We can have up, down, all these. We have a pentagon, or we can have a star. So those are our various types of points. So we can set up our graph to have any type that we want, and that's what this particular slide or example does right here. Going back to my right here, right there. As we look at this right here, we also can specify, and I didn't get into it, a line with a 3. So again, this is where, and let me just blow this, give this the full screen, so you can see what's going on here. As we look at this command here, we're going to plot right here y1, and y1 is just sine x. That's our basic right there, and we're going to specify a color of 50, 210. Notice that there's a divide by 255. That number has to be between 0 and 1. So I divided by 255 in order to make that to be the case. The largest number is 244. Now I could go through here and I can just make this a red line by just simply making these two 0 and this one 255. And I'll do that here. So because if I run this, if I go back to my plot right here, right there, we can see that this particular one is more green because it's RGB, right? So the green component is almost 1. The red component is very small, and the RGB, the blue component, is very, very small. So as we look at this right here, we can get a very different there. So yeah, we'll tweak these around, and I'll just copy them over and do them all at one time. The next one, again, we can also make them wider. The line width is another parameter that we have there. So as we look at our graph right there, we can see that And there's no easy way of doing this other than right there. Our first one is got a line width, and that's our green one, of 3. This one, the next one, right there, the last one is the one it's got the zeros right there. That's got a line width, but those are zeros. So if we made those 3, they would be very large. So we can identify the various points. So let's just go back here and let's just kind of tweak these a little bit. And again, I'm going to cheat because I'm going to grab this right here, and I'm going to just change this right here, and I'm just going to just change this to a color red right there, and I just grab that right, or I don't want to do that. I just want to grab these right here. Copy. Let's close these 2 fingers. And let's just paste that. And it doesn't like the red right there. Why doesn't it like the red? Right there. Actually, I think I got this command wrong. This command there that R should just be there by itself. Zooming, hard copy. This particular one doesn't give the red. I always just use, let's just, it stopped at this point right there. Let's just simply put the right there. Okay, other properties, hold, there, edge marker K. Oh, it's got to be in single quotes. Right there. That's what I left off, the single quotes right there. If not, we'll right there. Oh. So I can see what I'm doing here. Let's try this. If this doesn't work, then it won't be the first time I've and the reason is, I'll just fix that one line right here, is that I didn't close this quote. Doesn't like that there. Likes the color. Because if I put the bracket 1, 0, 0, that works perfectly fine. Okay. So evidently using the R, it doesn't like that well. That's probably why I never used the R. I probably fought through this once many years ago and realized that it was not worth fighting with. So now the line width, if I just go back here and change that to 1, notice that the line is very thin right there. So we can tweak with that there. And again, I can go through and probably just easier to do this. I can make this a green one. RGB, R1, right there. Well, actually, that's going to be 1-1. I didn't make that. That's why we can see that it's a funky looking yellow there. We can go back there and make that the 0 that I intended, and there's our green. So you can play with all these various ones. Again, we can come back here, and we can make them all 1s, and that should make it black. Right there. I'm going to make the width larger because it's a little hard to see. Oh, that makes it white. Right there. Oh. There's our black right there, 0, 0, 0. I knew it was 0, 0, 0, 1, 1, 1. Until it's been about almost a year since I played with MatLab. That's there. So we can also change our line style. We can pretty much put whatever we want in this here. Make this a plus. Oh. Right there. It doesn't like that one there. Bad. What did I break right here? Go back to my line styles on my slide. There, those are the examples. Line styles, example. Right there. Place the circular mark at the data point. Right there. Now you can plot without a line. Right there, that's essentially what we're doing. Right there. So you get kind of a feel for what we've got. Right there. Let's just stick to slideshow. Current slide. So what we've got here is that we've got colors, and we can place symbols in there. We can do all kinds of various things. So the plot is easy, right there. You've got full control. And if you look at the help, it'll give you all kinds of different examples. But the plotting, I'll be honest, I usually keep my plots fairly simple. That there. I don't spend a lot of time on setting these plots up. That there. Now, there's a lot more that we can do, and we're going to be talking about that right here. So let's kind of go through here. Other properties. That there. I don't spend hours trying to pretty up my plots by putting fancy lines. I just pick 2 or 3 basic colors and go with it. That there. You've got better things to do than spend hours trying to tweak a plot. And that's why you can see that I'm very comfortable with the plot command. Getting in there and trying to tweak it, I don't spend a lot of time. It's not worth it. That there. Because again, what you're using MATLAB for is you're doing research, you're doing analysis, and you want to see a quick and dirty plot. You know, when you stick the data in that there. You got a bunch of data in a file, which we'll talk about files, I think, a little bit later, where we can read data files and bring it into an array, and then plot the data from our file. Or we can generate data from math functions, which is what we're doing. Or we can type in our data manually, right there, which I'll do some examples of that here, right there. So again, here's another example here where we're just right there, and you put the window right here. This is another example right here. I'll just grab it and just right there. Copy, and just stick it in there. And let's just right here. There's our. Notice this time I used the term. Oh, what did I do? Because I used the term figure right there in order to just bring up the graph. I said t is equal from 0 to 2 pi, just like I did before. Now this time I use 20. I can do it a little bit differently there. I can that there. So again, I plotted that there. In this particular case, let's bring up the plot again. Let's close this plot right here. Bring up the plot here. Again, I did the hold on here. This first one is that we use the R. I copied that there. right here. So this is our red one, and we're using the little asterisk for our symbol right there. So we've combined a few of these right there. So we've got the dash, dot, asterisk. So this is this line right here, right there. We put our hold on, and then we put on our next graph, which is our dash with a 0, that there, right here. And then the next one is our square right here. So again, you can see the 3 lines very clearly, and then we put our hold on. So this is just another example, and I pulled these examples from various places, copied them from books and things like that there. I've used them, that there. One of the other things that we can do with this right here, I'm going to close this right here, right there. And the clear command just clears the memory here. So the clear, what is the command for clearing? Clear screen MATLAB. There's a very simple command, and I never remember it. Clear is the one I keep remembering, but that just clears all the data. Clear command window, clears all input function from the command window display. The clear. CL. Clear command window, CLC. CLC. Yeah, that's the one. That's the command. It's not one of those obvious ones. Clear is easy, right? CLC is not as obvious. CLC, that just clears that screen to where we don't have to look at all that garbage as I go between examples. So CLC, that there. But because clear does a different thing. Because if I say, for example, y equals 3, that shows y. If I type y, it does it. If I do clear and I hit y, it tells me it's undefined. Clear just clears out the memory right there. So what I wanted to do was clear off the display to where every time I do an example, you didn't have all that other stuff to look at right there. And that one's not as easy to remember. Now, have you done anything beyond the command window in MATLAB? I would think not, right? Everything's been in the command window right there. Because you can write what they call a script. And the script right here is basically like a program. So I'm deviating a little bit from there. And what I'm going to do here is I'm just going to go back to my slides and just grab one of my examples right here. This example is good. Copy. And this basically becomes a script right there. Right there. So that's a script right there. And I can save this. And this now saves as what they call an M file right there. So and it's stored in documents right there. And I'm just going to call this UniKL-1 right there. Oh, it doesn't like the -1. It doesn't like the 1 or the -1 right there. So some of these programs, to be honest, are very old in terms of how they interface with Windows. And MATLAB has been around since about Windows 4, I think. Because there was Windows 1, it sucked, it was horrible, didn't work very well, nobody bought it. That's there. Windows 2 came out, it sucked, it was horrible, nobody bought it. Windows 3 came out, it sucked, it was horrible. Windows 3.3 came out, all of a sudden they had something that worked. So Windows 3.3 was the first working version of Windows right there. And some of it was that Windows came from a project in Palo Alto, California, run by Xerox. Actually, Xerox invented Windows. Steve Jobs says that Apple did. Steve Jobs is a liar. Apple stole it just like Microsoft did. Microsoft stole it from Apple, but Apple stole it from Xerox. Which is the way things work in the technical world. Even Steve Jobs has been quoted to say that innovators borrow great ideas, but great innovators steal. And Apple stole the whole concept of Windows. So the first version of Windows, up to Windows 95, required a text-based operating system run in the background called DOS. And I know DOS was gone before any of you were born. That's there. But DOS only allowed file names up to 8 characters. You could not have spaces or anything like that. And that's why it's giving me that error, is because I used a character other than that. If I tried to use a name beyond 8, because they had these old programs that ran on versions of Windows that sat on top of that there, and they've never gone back and changed the code in certain parts of it. They just keep adding more code and fixing it to where it runs with new versions of Windows, and they keep improving the code, but certain little glitches in the code that go back to the old versions still hang. So, and that has nothing to do with, that won't be on any final project or anything, just kind of a background why you sometimes get these funny errors on file names. Because it looks like a good name to you, because you've never had to deal with DOS that limits your file names to only 8 characters, and you can't put stars and dashes and things like that there. So, all right, now I've saved this, so I can actually come back here, and I call that UniKL1, right? UniKL1. And see, what it does is it goes out there and it finds that file and just executes it. That's there. So I asked earlier if you've ever heard of an M file. That's there. And everyone said no. And the reason M files are so important is it saves me from a lot of typing. Because I can go back here and I can open this file. It may already still be open, or did I close it? Yeah, I closed it right there. Yeah, but I can open that file right there, and I can change things in that file and then go back to the command window and reopen and rerun that script out there. And it makes life a lot easier if you're doing multiple graphs, multiple problems, that I don't have to retype everything, which is one of the reasons I don't know the C command, by the way, because I typically work with an M file. And then when I work with the M file, I make my changes to the M file, I resave it, and then I go back to the command window and just rerun the M file. So if I go back here and I change this, for example, and I'm going to say T is equal to that there, and I'm going to plot the second one. This is T divided by 2 right there, because as you look at that there, let's just say I'm going to say 3x then. Right there, because I can edit this here 3 times, and I can save that, go back to here, and hit the up arrow, and see now I've changed my graph. Very simple right there. So it saves a lot of time for any of the problems that you're solving. To just create an M file and just dump your commands into the M file and just run it from there. So, and you notice that my background screen is not very messy at all. All I see is I just keep running the same M file over and over again, and I just go back and I just reopen that M file right here in the editor, and I can go through and make further changes. So I think from now on I'm going to operate out the M file just simply because it makes life a little bit easier. And then the other advantage of the M file is you save it for the next time you go, you log in, or you work for, you can save your M files if you're working on a project, for example, on a flash drive, and you can bring it in, stick it in, and the same files are there every time. You do have to copy it over, although there is a way that you can, and I don't remember because I always just, I'm used to working off of a laptop, not a lab machine. So some of the things there's a way that you could specify the path to where to look for the M files there. It's probably easier to just go ahead and copy it into the directory. And you'll find, if I hit the save as, you'll notice that it's under Documents on your PC in a directory called MatLab. That's where all your M files are. And I can open up any of my old M files, for example, right there. Oh, no, I don't want to do that. That there. I can open, say, here's a file that, I want to close this right here. Let me close everything here. All right, here's the file right here. And this happens to be a file that I created for another purpose right there. And what this is just to create what they call a digital filter. So again, it's something that I spent some time coming up with the order of the filter, the number of coefficients, blah, 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 and I don't want to retype that every time. So again, I can open, and you can see that I've got various other, junk, for example. I don't know what junk is right there. Well, junk is, it's a very similar type project that there, but this is one for designing right there. And I can run, this is called junk 1, right? So I can just type junk 1 right there. And it should plot a plot right there. Maybe it doesn't. Maybe it's junk 1. Oh, it does have a plot. Where's my plot at? Yeah, there's my plot right there. So, and actually, if you look at this particular one right here, is that this calls a function right here called FFT. And FFT stands for fast Fourier transform. It takes the signal and converts it from the time domain to the frequency domain. So what you're seeing on this plot right there is that I've got a signal at various places, and I'd have to, this graph doesn't show me what the actual frequencies are, but again, I'm not trying to get across how this program works, but just the fact that by running M files, I can write a series of commands and run it as a script right there. That's actually not supposed to be part of today's lecture, but I threw it in there simply because it makes the rest of the lecture go a lot easier. That there is that if I can operate out of using M files instead of having to worry about the command window. But anything you can do in the command window, you can do with a script. Now, the only thing I don't do with these scripts, and there's a way of doing it, I just have not bothered to ever do it. So if anyone's interested, I'll figure out how to do it. At there is have a place for input, because I'm always running this. I always have the script editor open and running it from the command at there. So, all right, let's move on here to my slides. And as I said, I'm going to just hit. And again, you just hit new script is the only way, is how you bring this up right there, is new script right there. So as I go through and look at the rest of my slides I have here, right there. Here's the example I had earlier. It's a very straightforward example right there. It has that there. All right, now semi-log is a very important function right there. And the reason semi-log is because when you take courses in filtering, and I don't know where you're at in your program, but at some point you're going to come up with something, and let me not use this. Let me use the problem with using this is, since I record this, then then you don't have access to it. So let me go back here and bring up, I should just leave it open right there. Let me close right there. I should have just left it open. I need to keep it on the, oh, there it is. It is there. Open window. There we go. Okay. That there. All right. I added a whole bunch of pages, didn't I? That there. Every time I kept hitting that. Okay. Let's just take something simple like this. Right here. B in, B out, right there. This is R, this is C, right, capacitor. This is a simple RC. This is a low-pass filter is what this is. So this is a low-pass filter. The output of this filter, if we ignore the output impedance of this here, in other words, the output impedance is whatever this is tied to out here. If we ignore that, we assume that this is going into a very high impedance op-amp circuit, for example, that there is that, and we ignore any of the input impedance from our source back here, Z right there. In other words, we have an ideal voltage source and an ideal load, which is not difficult to do when you do filter design, is that our output there is a simple voltage divider, right? The impedance of Z, or X of C, is equal to 1 over 2 pi FC, right? I can see the looks on people's faces. You're not lying to me. You've seen this before, right? The impedance of R, of course, is R is equal to R, right? Now, when we look at this particular circuit right here, the output is V out is equal to, and I'm going to call it X of C, and I'm going to put minus J there, right there. And it's going to be over R minus J X of C times V right there. So this is a simple low-pass filter right there. Now, if we plot this, the output of this filter right there, we plot that, and we're going to plot V out over V in other words, right there. And we're going to plot that with respect to frequency right there. You know, at some point right here, we're going to have, and I'm going to call it F of C, and we'll talk about F of C later. For the looks of people's faces, you probably have seen this before, but this happens to be the break point of the frequency right there. The output is going to be roughly 70% right there, and we'll get to why it's 70% here in a few minutes right there. So we're going to call that right there. Everything less than that, we're going to say is going to be equal to about 1. But at this point here, it's actually 70%, and it starts rolling off right there. Now this roll-off looks linear here. It's only linear because I'm plotting this here with a log scale. When I say a log scale, it means that this frequency right here, and actually, right, there I misdrew my graph here. Right here, it's supposed to be going down like this right here. We typically approximate it looking like this right here. In reality, it rolls off here. But what we plot here is we plot our gain logarithmically in dB right here. Our gain is in decimals there. And we plot our frequency in the fact that we're down minus 20 dB at 10 FC. We're down minus 40 dB at 100 FC. In other words, every division is 10 times the previous one right there. The next division is 100. So this is not a linear scale. This is a logarithmic scale right there. And the example that I've got doesn't show exactly a frequency response, but we can plot here, and I may as well go ahead and finish this example that there and that there. But if we were to plot this here, first off, let's define FC is the point where is the frequency where XC equals R. We're going to define that as the frequency right there. We define that as our frequency. And we'll do some reverse analysis to why this is an important frequency right there. So if we define that first, so we simply say that R equals 1 over 2 pi FC. Now, I should point out here that I'm putting, these are the absolute magnitudes, because there is a phase shift of minus 90 degrees on the capacitive inductance, or capacitive reactance right there. So we define that there, and what we end up with is FC is equal to 1 over 2 pi RC right there. That's our very simple calculation for calculating the critical frequency of this particular circuit there. And again, I'm hoping this is review. I think it is, looking at a few people shaking their head right there. So, you know, and there's ways of doing this with calculus that is much nastier, but the algebraic approach works for this particular right there. So if we look at this right here, V out over V in right there, is equal to, first off, we said V out is equal to X of C over R minus J X of C times V in, right there. Now, if we look at the absolute magnitude of that right there, and that's what we're looking at when we're doing our we're calling this Bode plotting right there. And again, I'm reviewing this simply to show how this then comes back into MATLAB. If we do this, this becomes X of C over the square root of R squared plus X of C squared, right? Because whenever we look at a complex number, its value is going to be, because a complex number, again, I know I'm reviewing a lot of that, but we're looking at, here's a complex vector right there. It's got a real component right here. This is the real component. This is the imaginary component right there. So it's got a phase angle right here, theta, right there. And it's got a magnitude. Now this is the right triangle, so we've got, here's IM. We use good old Pythagorean theorem, which simply says the magnitude is equal to the square root of the real part squared plus the imaginary part squared. So we're just applying Pythagorean theorem on this right here. So we're going to go back here and we can rewrite this expression in terms of frequency there. And I'm not going to spend a lot of time on this. This is a subject for another course. But if we did this, we would get some kind of function that we would say that V out over V in right there is equal to some function of F divided by FC right there. So it's a function divided by FC. And if we were to plot this right here, and we were to take the log of that, and we take 20 times of that right there, times this gain right there, and we were to plot that on a logarithmic scale, we get this really nice, neat graph that looks like this right here. Right there. So it's important that we know how to plot logarithmically. So I'm going to just go through some examples that I stole from other sources. You could probably find an example of doing this there. You know, that's an exercise for, for the lab, actually, to be honest with you. To rewrite is to take this expression right here, and I'm going to recommend to Boz that she does this, to take this expression right here. Let me just do it as a new page right here. V out over V in is equal to X of C over the square root of R plus squared plus X of C squared. And then keep in mind that we have a particular frequency, FC is equal to 1 over 2 pi RC, right? So then I can say R is equal to 1 over 2 pi FC right there. There, we can stick that in there, because you got to remember that R is going to change right there. And we can also say that F, if we do this here, that R drops out of will drop out of the formula that says that XC is equal to 1 over 2 pi, and then we're going to say 1 over 2 pi FCC right there. Right there. 1 over 2 pi. That's R. Excuse me, what am I doing here? Now I've completely backed myself into a corner. Because what we're going to then say is that, that XC, of course, is going to be it's going to remain the same right there. 1 over 2 pi FC right there. But what we're going to find is you can rewrite this, and this is an algebraic problem that you need to solve, that you end up where the R's drop out and the C's drop out, and you're left with this expression being something over over, you know, F and FC right there. So then when you did that, you would then plot on this graph 20 times the log of, and I'm going to call it V out over V end, right there. You're going to plot that on one side, and that's in dB. And then you're going to plot this side frequency, and this scale needs to be in logarithmic form. So this needs to be 1 hertz, 10 hertz, 100 hertz, 1K, like this right here. So we need to plot this with a log scale. So going back to my slides, we have a semi-log right there. So what we've got here, and let me just kind of grab this. I'm going to do like I did before. This time I'm going to put it into an M file. Copy. Go back to MATLAB. Right here. Right here. In this particular case, I just created some data right there. You know, again, don't worry about this. This is a couple of Bessel functions right there. And what we've done here is that we've, at this point here, I've set a figure. And here I'm going to plot right here EB with CRB right there. Hold on, and I'm going to plot EB right there. And then we're going to put some labels on here. This is the title of our graph. This labels our x-axis. This labels our y-axis. And if we plot this right here, let me just go save this. Save as, and I'm going to call it UniKL2 right there. Go back here. Right there. What we're seeing here is, as we look at this here, notice that this happens to start at 1, 1/10, 100, 1,000 right here. So this is going this direction. Now, if I reverse the two, I could do, and you'll see that this is logarithmic. Now, if I go back to this right here, I'm going to reverse the two of these, because most of the time when I plot graphs, I want the x-axis to be semi-log, be the logarithmic, and I want the y-axis to be, you know, normal. So if I go back to my M file, and right here, and what I'm going to do, simply do there is, right here, is I'm just going to reverse these right here. EB right here, and if I just reverse these right here. Right here, same thing here. Right here. Right there. You notice here, this is my axes. I reversed them, but I didn't change the axes or change the labels. Right there. Right here. You'll notice that, again, that looks strange, because it's still doing the axes this way. What did I do wrong here? EB title X here. Oh, this is what's telling it what axes to. Right there. Does everyone see what I changed? You know, one of these said that I want semi-log Y and semi-log X. That's what it tells you which axes you want to be logarithmic. Right there. Let me close all these graphs. Right here. Oh. Yeah, there we go. That's what I was expecting to see. Right there. So as we look at this command here, I'm going to bring this up in the editor right here. As we look at this command right here, what we've done is we've just typed in some data. And this could be where you put your formula that you're supposed to that you want to come up with. There, that would compare F to FC right there. You would plot there, but you would generate your data. So how the data comes from, we don't care. You can read it from a file. You could do however you want to get that data. In this particular case, I just read the data in from, I just typed it in right there from doing calculations. Then we're going to just simply do a figure, which is this command is actually optional, as I that there. Then we're going to plot. We're going to create a plot, and it's a semi-log plot. This is the command that actually replaces the plot command, and we're going to plot on the x-axis semi-log. It's going to be logarithmic. If we want the y-axis, we would say semi-log y. That's what it was before. That's what it was out there. So we tell what axis we want to be logarithmic. We specify what we want on the x-axis. In this particular case, SER, which is whatever that is. That's what we read in off the table. And then we're going to plot on the y-axis EB, and that's our decimal right there. That's similar to what you would do with our calculations before. You would calculate that there. And then we want this to be blue with zeros and a dash there. Now this specifies the format. If you change this to say a G right there, and actually you can run it from right here. See? Yeah, you don't even have to go back to the command window. You can just hit the run button right there. So, I can change that to right there. This is goes back to that there. So we could put that back to a star, for example, at this particular point. Right there. Nope, it doesn't like the star. What was that? That was the dash. Oh, this is the star. See, now that puts a dime in there. It makes it green right there. So but this is out there. I completely forgot that starting with version, I think 2011, they added the run button to the M file editor. So this is really the way to do it. So that just adds your logarithmic scale. And there's many times in the engineering world, especially when you're dealing with communications and frequency, that you use a logarithmic scale. And a completely side note to that is that many things in nature are logarithmic in nature. One example of that is sound. The human ear hears from roughly 20 hertz. That's the lowest, deepest sound you can hear. That's the bass guitar if you're a rock band. That there. All the way to the highest sound, which is a 20 kilohertz, which is the highest, electric guitar tightest string at the smallest fret, might be somewhere right around 12 or 13 kilohertz right there. So that's so your bass is your lower frequency, your treble is your high frequency, and that's a logarithmic scale. So whenever you look at the frequency response of, say, and it's not as popular today as my age, back when amplifiers weren't perfect, so people would buy amplifiers looking at the frequency response curves. And you would buy speakers, and the ideal speaker right there, or an ideal amplifier, either one, you would see this range from 20 hertz to 20 kHz. You would see a flat line there, and then it would roll off before and after that there. If you had something that did this, means that certain frequencies were amplified. If you had something that looks like this, certain frequencies were attenuated. But in an ideal speaker or amplifier, you would have a perfectly flat line. between 20 hertz and 20 kilohertz. You didn't care about anything below 20 hertz because it was below the range of the human ear. You didn't care about anything above the 20 kilohertz because that was above the range of the human ear. Now, certain animals, dogs, I realize most people here, nobody in this room owns a dog, but dogs can hear above 20 kilohertz. So they make whistles that, I haven't seen them for years, that you would stand outside your door and call your dog home, that would have a very high frequency that nobody else could hear but dogs. Unfortunately, every dog in the neighborhood could hear it, so you could have 20 dogs running to your front door. But the thing is that dogs can hear much higher frequencies than humans can hear. As we get older, everybody here probably hears pretty well up to 20 kilohertz. I think the oldest person in this room is probably 21 or 22. I'm 58, so my hearing tends to move back to here, maybe to 16 kHz or less. As you get older, the hairs in your ear, which is sensitive to hearing, become a little bit less responsive, and what goes first is the higher frequencies right there. But these scales are, the human ear is based on, I said when the battery went dead, class was over, right? We're getting close to that point there, right there. So as we look at the human ear, it's a logarithmic function. Sound intensity is a logarithmic function. In other words, in order to, again, I'm talking to the generation that is iPods or iPhones. iPods you don't even use. You use iPhones, right? And no one bothers with the iPod. Or you have an Android Galaxy phone. I mean, I've got one too, so I'm not picking on anybody there. But back in and people still do it. If you have an amplifier for your home, a 50-watt amplifier would generate a certain level of sound with a certain type of speaker. If you wanted to get a noticeably higher level of sound, you actually have to double the frequency size of the amplifier. So you have to go from a 50-watt amplifier to a 100-watt amplifier to hear an appreciable difference in that there. If you go from a 50-watt to a 60-watt, you're wasting your money. You won't hear a difference. You have to jump up to at least double in order to hear a significant. So people that battle that, I've got a 60-watt and I got a 50, they're all within the same order of magnitude. It's going to sound pretty much the same. Same thing with light bulbs. If you've got a 50-watt light bulb, you need to go to a 100-watt light bulb to see a significant change in the light. You might see a little bit, and it's very little. To see a significant change, which is a 3 dB change in power, that's there. You need to double the power. So a lot of things in nature are logarithmic. Is what I'm trying to say. That's why we see these logarithmic scales so often, right there. So I think that's going to pretty much wrap where I'm at here. Let me see. Log. That does the same thing. This is just happens to be an amplifier. This particular one we're plotting, both scales are logarithmic in this particular case right here, right there. And let me just slideshow. I'm not going to spend a lot of time on it right there. But you'll notice right here that instead of saying semi-log, we just simply, and class is definitely over at there. So I need to put this on the charger,